Okay, hi class. So we're moving on to 6.2. Hopefully my computer troubles are going to go away, but we'll see. So we're just going to graph the other four functions: tan, secant, cosecant, and cotangent. And I'm really not particularly picky about you graphing these with a super amount of detail by hand. We're going to use our calculator a lot to help us, which is fine. We really just want to understand why the graphs have the shape that they do. And then we'll use our calculators to help us as well. But so I'm not going to when I'm going to have you graph, I'm not going to have you be as detailed as I am when I'm starting out here. I'm going to make a table of values for us just to help you understand why this is happening. But after that, once we get used to it, you can just go ahead and jump right in. So first things first, remember the definition of tangent. It's y over x. That's on the unit circle. But in general, tangent is also opposite over adjacent. But another way to think about tangent is that it's actually just sine over cosine. So what that means is that whatever the angle x is, the tangent just going to be the ratio of the sine over the cosine. Okay, and I already filled some of these out for you. Again, I'm not going to take the time to explain, this is just going to be, you take pi over 3 and you plug it into sine, you divide it by cosine, you get negative root 3. And negative root 3, root 3, all that stuff, okay? At 0, it's going to be 0 because sine of 0 is 0, cosine of 0 is 1. At negative pi over 4, it's going to be, so that's down here, and that's root 2 over 2, comma negative root 2 over 2, and so that's going to be negative 1. Here's going to be 1 because they're both positive, root 2 over 2. And at the poles, these are actually undefined. Why is that? Well, let's see. Take the pi over 2, for instance. The point right here is 0, comma 1. And if tangent is defined as the sine over the cosine, that means tangent of pi over 2 is going to be 1 divided by 0, and that's undefined. Same thing with the negative pi over 2. It's also going to be undefined. It will be negative 1 divided by 0. Now what happens is that as you get closer and closer, you end up getting this vertical asymptote. So we have these vertical asymptotes at all the pi over 2's, all the multiples of pi over 2. Multiples of pi over 2. Okay, and so for instance, like when we were talking about like the end behavior, as x approaches pi over 2 from the left, tangent of x approaches. So let's take a look. Here's pi over 2. As I approach pi over 2 from the left, it looks like it shoots off to infinity. Okay, and if we did say as x approaches negative pi over 2 from the right, so that would be over here. As it approaches from the right, where does the graph go? It looks like tangent x goes to negative infinity. So we're going to have these vertical asymptotes. So they have these vertical asymptotes. Okay, whenever x is equal to a multiple of pi over 2. So I'm going to write a multiple of pi over 2. So that means, like negative pi over 2, pi over 2, 3 pi over 2, 5 pi over 2, etc. Okay, so anytime, and just go back to the unit circle if it helps you, just anytime you're on the north and south pole, you're going to have this tangent that's going to be undefined, okay? And so that's why these graphs, they're different. They look different than sine and cosine. They only have a smaller period, so the period here is negative pi over 2 to pi over 2, so it's only a period of pi. So period of pi. Okay, they have these vertical asymptotes at the poles, pi over 2 and negative pi over 2, etc. 3 pi over 2, negative 3 pi over 2. Okay. All right. So, anyways, so that is all summarized here in this table. When you have the graph that's y is equal to a tan bx, okay, we're only going to be dealing with stuff that looks like this. We're not going to be dealing with shifts like a plus c, a plus d, or anything like that. So we're just going to be dealing with the more simplified version of tan. And if we have this, then the stretching factor is not called the amplitude anymore. It's called the stretching factor, and the reason is that this doesn't have an amplitude because it doesn't have a height. You know, there's no finite height because it goes off to infinity. So instead of calling it amplitude, because there's no distance between the top, because there is no top and there is no bottom, we just call that the stretching factor. The period is defined as pi divided by the absolute value of b. And again, that's because if b is 1, the period should be pi. So that's why it's pi and not 2 pi. We're going to follow along with these formulas here. The range is that, the domain is that, and the asymptotes occur here. Again, we're just going to plug and chug into the equations here, and I'm going to provide these boxes for you, so you'll have these on the exam. Everything in the boxes today you'll have on exam. I have a little cheat sheet. Okay, so let's scratch a graph of one period of the function y equals 0.5. So remember the general graph is y is equal to a tan bx. Okay, and remember that the stretching factor is the absolute value of a. So in this case, a is 0.5, and so that means the stretching factor, okay, and that's going to be the absolute value of a, which is the absolute value of 0.5, which is going to be 0.5. What that's going to do is just kind of shrink the graph a little bit. You'll see the period is going to be p is equal to pi over b. So here the b was pi over 2. And so it's going to be pi divided by the absolute value of pi over 2, which is pi over 2, which becomes, you multiply that up, 2 divided by pi, and those cancel, you get 2. So the period's 2. And the domain is going to be all these guys, and we're going to just take a look. This easiest, we only want to graph one period anyway, so just go over here, take a look at our graph. Okay. Alright. And I want us to get practice using a calculator too, because we want to make sure that we can do it. So it's 0.5 times tangent, I'll put that in parentheses, pi divided by 2 times x. Okay. Now check it out. Our calculator is actually lying to us here. These jagged lines right here are actually asymptotes, and it's not really understanding how you can show it. So if we zoom in a little bit, it'll be a little bit better, but it's not going to be great. There you go. So this is the graph. Now, the newer calculators don't do this vertical line. They'll just leave it blank, but this is what the calculator is trying to say, that this is a vertical asymptote. And so that means that we have these vertical asymptotes at these values, which are about pi over 4. We can find that because that's going to be, so the vertical asymptote, according to the formula, is going to be x is equal to pi over 2 times, again, b was pi over 2, okay, plus pi over 2, okay, times k. K here can be whatever we want, so I'm just going to choose k to be a 1, so just make it a 1. In the formula, k can be an integer. Integer is just a whole number. Okay, and so what this gives me is the 2's cancel, and so I'm left with pi over pi plus pi times 2 over pi, and so we're left with, that's 1, so we're left with 1 plus 2, which is 3. So I'm going to have asymptote here at 3. If I let k be 0, then also this is just going to be pi over pi, which is 1. So I have another asymptote here. So in this problem, I'm going to have asymptotes at -1, 1, 3. Okay, that's the pattern. Anyways, we just only want to do one period, so I'll just do it right here, in between here and here. And the graph, if we go back, it just looks like it goes right through 0. So it goes, and that's because tangent always goes through 0. Like that. And we only do one period, so that's good. All right. So I am going to go kind of faster on this one because, again, don't get freaked out too much. Just know how to use the box here, and also, when it comes to the graphing part, you can just kind of sketch it using the calculator. That's fine. I'm not going to have you know the parent shape of tangent and then have to be able to do all the shifting and stuff like that. Cotangent looks same as tangent, except it's flipped. It's a left-right flip, okay? And that's because cotangent is defined as cosine over sine. And so these have this shift. So the tangent graph, cotangent graph, excuse me, will be undefined and have vertical asymptotes whenever x is equal to actually 0, pi, 2 pi, 3 pi, etc. Okay, or negative pi, negative 2 pi, negative 3 pi, okay, etc. And the reason for that is that, again, it's a unicircle. When you have the unicircle here, I'm trying to draw it here, it's going to have vertical asymptote whenever sine is 0. Sine is 0 only here and here. So whenever sine is 0, that's when your cotangent graph is going to have a vertical asymptote. And that angle is 0 pi, 1 pi, 2 pi, 3 pi, 4 pi, 5 pi, 6 pi. And same thing going negative. Okay. So let's get your graph in one period of the function here. Okay. So again, the stretching factor, absolute value of a is the absolute value of 3, so it's 3. So that's the stretching factor. The period is going to be pi. So cotangents also have a period of pi. This period is going to be pi divided by the b is here. It's the coefficient from the x, pi over 4. So that's the period. It's shrunk. Okay. The domain is that x can't be these multiples of pi, and the asymptotes, the vertical asymptotes, or no, horizontal, is going to be pi over b, so pi over 4 again, times k. Okay, and you can let k be whatever whole number you want. So if you let k equal 0, we have a vertical asymptote at 0. If you let k equal 1, we'll have a vertical asymptote at pi over 4 times 1, pi over 4. If you let k equal 2, you'll have x is equal to pi over 4 times 2, which will be pi over 2. Okay, and those are some of the vertical asymptotes. And then we just take a look at the graph. Okay, and go here, go back here. Now I definitely want to use the calculator here because I want to hash that there is no cotangent button on the calculator, but we can get cotangent by just doing the reciprocal of tangent. So 3 cotangent is the same thing as 3 over tangent of 4x. So if I go back over here and I go 3 divided by tangent of 4x, this is what allows me, I don't need that, this is what allows me to actually write it in as 3 cotangent 4x. So this is equivalent to saying 3 times cotangent of 4x. It's just, this is the way we can do it on the calculator. So we go here, we got these graphs, and I'm going to zoom out a little bit. Actually, you can go zoom Trig here. Sometimes it makes it good. Yeah, not super helpful. That's too much. Let me zoom out a little bit. Standard. Not helping a super lot. So I actually have to zoom in quite a bit. Let me zoom in to get the kind of general shape. That's a little bit better. You know what I can do here actually is change the window too. I can make the Y scale a little bit different. -10 to 10. Graph that now. There you go. That's the shape I was looking for. So cotangent has this nice little pretty, these lines again are the vertical asymptotes, and they're happening at these values, pi over 4, pi over 2, and 0. 0 is a vertical asymptote. And then it's supposed to have this nice little kind of, I think it's kind of elegant little shape right there. And so our graph is going to look like that. So it's going to look like, go back here. So to the left of 0, it's going down like that. So I only wanted one period on the problem, but you can pick any of these as your periods. So x is 0, x is pi over 4, x would be pi over 2. Okay, and that's the general shape. Ooh, that was a really bad one. Okay, disregard that, my bad, but these are more accurate. Okay, so the last ones we want to do are secant and cosecant, and again, we'll have the tables, the boxes here, so you don't have to have these memorized, but just in case, you know, this is what's going on here. And again, the connection of why these graphs look like this is that, let's talk about what secant was again, just to remind us. Okay, remember, secant of x is defined as 1 over cosine of x. So whenever cosine is going to be 0, I'm going to have a vertical asymptote. And so cosine has 0 whenever you're at the poles, at pi over 2 and negative pi over 2. So that's why at the poles here, at negative 3 pi over 2, 3 pi over 2, also here this is x is pi over 2, I have these vertical asymptotes. Okay? And the really cool kind of picture that I like is that this is the graph of cosine in blue. Secant is actually just this ratio right here. And so as cosine gets close to 0, which is right here and right here, this graph actually shoots off to infinity. Like that. So this thing that I'm drawing in red right now, that's the secant graph. Okay. And so these have these little bullhorns that go up and down like that. And the reason that they shoot off to infinity again is because it has a vertical asymptotes here, because that's when cosine approaches 0. And it's the same thing with cosecant. Remember, cosecant is defined as 1 over sine x. And so that means that it's going to have a vertical asymptote whenever sine is 0. And sine is 0 when you at 0 and pi and 2 pi and 3 pi. So that's why these are the vertical asymptotes for sine. For cosecant, which is 1 over sine. And again, it's connected here because they're equal when it's there, but otherwise it's the ratio, and this ratio will shoot off to infinity as as the sine value gets close to 0. Okay. Anyways, like I said, I'm not super all about that life, about getting really, really deep into the details, okay? So we can just jump right into graphing a period. We can just go ahead and use our calculator. So we go here to y. So we want 2.5. Now there's no secant button on our calculator, but remember that this is secant is just 1 divided by cosine. So if we just write 2.5 divided by cosine of 0.4x, like that, and then we go ahead and hit graph, and we get our drawing. And I zoomed out a little bad here, so what I'm going to have to do, I'm going to have to go to standard, I think. Should be fine. Yeah, here we go. Okay. The biggest it gets, the smallest it gets is 2.5, and that comes from this. That's the smallest it can get. And it does shoot off to infinity, so when you have this graph, and we can work out what those vertical asymptotes are according to this formula. So the vertical asymptote is going to equal, colon, x is going to equal pi over 2 times the absolute value of b. B here is 0.4, so it's 0.4. It's positive already, so I don't need to take the absolute value, times k. And I can let k be 0, k be 1. So this tells me if k is 0, then that one vertical asymptote is right here, that x equals 0. But if I simplify that, this is going to be pi over 0.8. Okay. So if, for instance, if I let pi k equal 1, I'm going to get pi over 0.8 and pi over 0.4 and all this stuff. So you get these different values. So this would be pi over 0.8. Okay, you get these vertical asymptotes, and that's what we're getting here. And the graph looks like this. So, and then it shoots down here, and the smallest it gets is negative 2.5, and the biggest it gets is 2.5. And that's one period, because a period is where the graph starts repeating itself, and it doesn't get, so it repeats itself after this, like that. And again, we can use our calculator to help us with this. You can also use Desmos online, which is nice, just on a test you can't. But I'm going to be, like I said, I'm not testing so much that you know all the super ins and outs. You are going to have these boxes for you, but just to know the general shape. And so don't be stressed out too much about this section. It's just going to be understanding why we have these little bullhorns and the vertical asymptotes and stuff like that. And the last one is cosecant. So we go here, we want -3, and remember there's no button for cosecant, but cosecant is 1 over sine, so we just divide by sine. Sine of 4x. Okay, and there you go. Graph that guy. And I'm going to have to change this mode, this window, because it's not giving enough detail. So I'll zoom in a little bit. Not really helping. So what I'm probably going to have to do is maybe try Trig here, see if that's going to work. Otherwise I'll have to change the window myself. Yeah, not super helpful calculator. So a lot of times the calculator doesn't really know what to do. So we're going to have to go in, change the window a little bit. I don't need that much here, so maybe like -4 to 4. And the scale can be 1. The Y min. Yeah, I definitely need at least that. Maybe bigger, -10 to 10. That worked last time. There you go, that's better. Okay, so we're seeing kind of the shape of the graph, and you know what, I can change the window too. I don't need this many x's, so maybe like -2. I can make these bigger too. 15. 15. Okay, let's try that. There you go, much smoother, much nicer. Yeah, so that's what the graph looks like. It has these vertical asymptotes at 0, and we can find those vertical asymptotes. So the vertical asymptote again will be x is equal to, okay, according to this formula, the vertical asymptotes occur at pi over b times k, and so that's going to be pi over b. Oh, you know what, folks? I'm sorry. I was looking at the wrong box when I did secant, so this is a little wrong. It should have been, no, I have it. Okay, pi over 2b, that's right. Good. Cosecant's pi over b. And so it's going to be just pi over 4 times k. And so when k is 0, x is equal to 0. When k is 1, x is equal to just pi over 4. When k is 2, x is equal to pi over 4 times 2, which is pi over 2. Okay, and so these are some of our asymptotes. X equals 0, x equals pi over 4. X equals pi over 2. It's not to scale. And so we have these graphs. And so to the left here, it's going to be, in between here, it's going to be going down, and then it's like this. So that. And the biggest or smallest it gets is right here. So that's going to be 3 and -3. Okay, and then the pattern continues. And it goes like that. These guys do repeat, they're periodic. They just have these asymptotes, these walls, and so they stop, they're not as connected. They're not connected like sine or cosine. They're not continuous. Okay, so that's that. Thanks for watching, and we'll catch you next time.